In September 2023, a hurricane named Lee was barreling toward the Atlantic coast. Traditional supercomputers, machines that cost $80 million and fill entire buildings, couldn't agree on where it would hit. But a single AI chip, running a program that takes less than 60 seconds, predicted the exact landfall location in Nova Scotia, 9 days before it happened. Today, I'm going to show you how weather prediction actually works, why we've been doing it wrong for decades, and how a neural network with fewer parameters than your smartphone's photo app just embarrassed the most expensive scientific instruments on Earth. But here's what's really going to blow your mind. The implications go way beyond weather. By the end of this video, you'll understand a fundamental shift happening in science right now, one that's making physicists genuinely uncomfortable. Let's start with a question that seems simple but isn't. Why is weather so hard to predict? You'd think we'd have figured this out by now. We can land robots on Mars. We can detect gravitational waves from black holes colliding billions of light years away. But ask a meteorologist what the weather will be like 2 weeks from now, and they'll basically shrug. The reason comes down to something called chaos theory. And no, I don't mean chaos like your closet. I mean mathematical chaos. In 1961, a meteorologist named Edward Lorenz was running weather simulations on an early computer. He wanted to repeat a simulation, so he typed in the starting conditions again. But to save time, he rounded one number from 0.506127 to 0.506. That tiny difference, less than 1 part in 1,000, completely changed the simulated weather pattern. After a few simulated days, the two forecasts looked nothing alike. This became known as the butterfly effect, the idea that a butterfly flapping its wings in Brazil could, through a chain of cause and effect, trigger a tornado in Texas weeks later. Now, here's the crucial part. Weather isn't random. It follows the laws of physics perfectly. Every air molecule, every water droplet, every ray of sunshine obeys Newton's laws and thermodynamics with perfect precision. The problem is that the atmosphere is what mathematicians call a chaotic system. Tiny measurement errors get amplified exponentially over time. Even if you could measure the position and velocity of every molecule in the atmosphere, which you obviously can't, you need infinite precision to predict the weather indefinitely. So weather prediction has a fundamental time limit, not because we're bad at it, but because the universe itself puts a cap on how far ahead we can see. For about a century now, the solution has been brute force physics. We call this numerical weather prediction, or NWP, and it's one of the most computationally intensive tasks humanity has ever attempted. Here's how it works. First, imagine wrapping the entire Earth in a three-dimensional grid. Each cell in this grid is about 9 to 25 kilometers across and extend from the surface up through the atmosphere in layers. Every 6 hours, weather agencies around the world collect millions of measurements. Temperatures from weather stations, wind speed from aircraft, humidity readings from satellites, pressure data from ships at sea. All of this gets fed into the starting conditions of the model. Then comes the hard part. For every single grid cell, and there are millions of them, you have to solve a series of differential equations that describe how air flows, how heat transfers, how water evaporates and condenses, how radiation from the sun interacts with the atmosphere. These equations are called the primitive equations of atmosphere physics. And when I say primitive, I don't mean simple. I mean fundamental. They're based on conservation of mass, conservation of energy, conservation of momentum, and the ideal gas law. Now stop and think about this for a second. You're trying to simulate the physics of a fluid air that wraps around an entire planet, is heated unevenly by the sun, is blocked by mountains, is influenced by oceans, and contains water that constantly changes between solid, liquid, and gas. And you want to do this accurately, for millions of grid cells, for every 6-hour step forward in time, for forecasts stretching 10 to 15 days into the future. This is why weather forecasting requires some of the most powerful computers on Earth. The European Center for Medium-Range Weather Forecasts, ECMWF for short, operates out of a facility in Bologna, Italy that cost about 80 million euros. They run 4 Otto's Bolzano supercomputers working in parallel. Every single forecast, just one 10-day prediction, requires about an hour of computation time, using thousands of processors working simultaneously. They're solving millions of equations, running the simulation forward in 6-hour increments, adjusting for new data, and generating predictions at multiple confidence levels. And the energy cost is staggering. We're talking about enough electricity to power small towns, running continuously, just to tell you whether it'll rain on your wedding day. But here's what's remarkable. It works. Sort of. Back in the 1950s, a 3-day forecast was about as accurate as just guessing that tomorrow's weather would be the same as today's. Now, thanks to better models, better data, and faster computers, a 5-day forecast today is about as accurate as a 3-day forecast was in the 1990s. We've gained about 1 day of accurate forecasting every decade since the 1980s. That's actually pretty impressive. But there's a catch. Improving further is getting exponentially harder. To double the resolution of a weather model, to make those grid cells twice as small, you need roughly 10 times more computing power. Each incremental improvement requires building bigger, more expensive supercomputers and burning more energy. We're approaching a wall, and that wall is made of physics and economics. Now, I want you to hold all of that in your mind. The grid cells, the primitive equations, the billion-dollar supercomputers, because I'm about to introduce you to something completely different. In November 2023, Google DeepMind published a paper in the journal Science that made meteorologists do a double take. They announced a system called GraphCast, and its performance was almost embarrassing. GraphCast can produce a 10-day global weather forecast in under 60 seconds. Not on a supercomputer. On a single Google TPU V4 chip. 60 seconds. Compare that to the hour required by traditional supercomputers. But speed doesn't matter if you're wrong. So here's the real headline. When tested against ECMWF's high-resolution forecast, the gold standard of weather prediction, GraphCast outperformed it on 90.3% of the metrics they tested. We're talking about 1,380 different verification targets. Temperature at various heights, wind speed, humidity, pressure. Across the board, the AI won. Now, I know what you're thinking. How is this possible? How can a single chip running for 1 minute beat massive supercomputers running for an hour? The answer gets to the heart of what artificial intelligence actually is, and it might change how you think about computation forever. Traditional weather models are physics simulations. They take the laws of thermodynamics and fluid dynamics, translate them into equations, and solve those equations step by step. They're essentially asking, given the current state, what do the laws of physics say should happen next? GraphCast does something completely different. It asks, given millions of examples of what the atmosphere actually did in the past, what patterns can I learn that will let me predict what happens next? The researchers at DeepMind trained GraphCast on 39 years of historical weather data from 1979 to 2017. This came from something called ERA5, which is ECMWF's reanalysis dataset. Basically, their best reconstruction of what the weather actually was at every point on Earth for the past 4 decades. That's about 1 million hours of global weather patterns. Every sunrise, every storm, every heat wave, every cold snap, all encoded into data. GraphCast looked at all of this and learned relationships that no human ever wrote down. It learned that when pressure drops in a certain way over the North Atlantic, temperatures tend to shift in a particular pattern across Europe a few days later. It learned that certain cloud formations in the Pacific correlate with rainfall patterns in South America. And here's what's kind of wild. It didn't need to know any physics to do this. The neural network has no concept of thermodynamics. It doesn't know what water is. It doesn't know that heat rises. It just learns statistical patterns from examples. But here's the technical detail that makes GraphCast special. And pay attention because this is clever. Traditional neural networks, like the ones used for image recognition process data in a grid, that works great for photographs, which are literally grids of pixels. But the Earth is a sphere, not a flat grid. GraphCast uses something called a graph neural network. Instead of arranging data in rows and columns, it treats each measurement point as a node in a network connected to its neighbors. This lets it handle the curved surface of the Earth naturally, without the distortions you'd get from trying to flatten a globe into a rectangle. The whole system has only 36.7 million parameters. To put that in perspective, GPT-4, the AI behind ChatGPT, has an estimated 1.7 trillion parameters. GraphCast is less than 1/50th of 1% the size of a large language model, and it's beating billion-dollar physics simulations. Now, here's where I need to pause and make something clear because this is where the nuance matters. GraphCast is not replacing traditional weather models. Not yet, anyway. There are still things it can't do well. For example, it struggles with rare extreme events, things that don't appear often in the training data. If there's only been one Category 5 hurricane with a certain unusual track in the past 39 years, GraphCast might not handle a similar storm well because it hasn't seen enough examples. It also doesn't give you confidence intervals in the same way traditional models do. Meteorologists run physics models multiple times with slightly different starting conditions to see how much the forecasts diverge. This tells them how confident to be in the prediction. GraphCast just gives you one answer. And perhaps most importantly, GraphCast was trained on data that came from traditional physics models. ERA-5 isn't raw observations. It's observations that have been processed and filled in using the very physics simulations that GraphCast is now competing with. In a sense, GraphCast learned to imitate physics models, then somehow exceeded them. But even with these caveats, the implications are profound. Let me give you a concrete example. Remember Hurricane Lee? In early September 2023, the storm was still forming in the Atlantic. Traditional models were showing what meteorologists call a spaghetti plot, multiple possible tracks spreading out like strands of spaghetti across the map. Some models had it hitting Bermuda. Some had it curving out to sea. Some had it heading for New England. GraphCast said it was going to hit Nova Scotia 9 days before it happened, while the supercomputers were still debating. And when September 16th arrived, Hurricane Lee made landfall in Nova Scotia, almost exactly where GraphCast predicted. This wasn't a lucky guess. The researchers at DeepMind tested GraphCast on cyclone tracking specifically. For tropical cyclones up to 72 hours out, it outperformed traditional methods by a significant margin. For some storms, it correctly predicted the track nearly a week in advance with precision that would have been considered impossible just a few years ago. Now I want to zoom out because what's happening with weather prediction is part of a much larger story. And this story is making some scientists genuinely nervous. For centuries, science has worked through what we might call the understanding paradigm. You observe the world, form hypotheses about how it works, express those hypotheses as mathematical laws, and use those laws to make predictions. Understanding comes first. Prediction follows. But AI is flipping this around. With machine learning, prediction comes first. Understanding, if it comes at all, might follow later, or might not come at all. GraphCast doesn't understand weather. It can't explain to you why a cold front forms or what makes a hurricane strengthen. It just knows that when the data looks like this, the weather tends to do that. It's pattern matching at a scale that happens to exceed physics simulation in practical accuracy. This bothers some scientists deeply. If your model doesn't understand the underlying physics, how can you trust it in new situations? What happens when climate change creates weather patterns that never existed in the training data? These are real concerns, but there's a counter-argument that I find compelling. Our physics models aren't perfect either. They're full of approximations. They can't simulate every air molecule individually, so they approximate. They can't perfectly model how clouds form at the microscopic level, so they use statistical estimates. They can't capture every interaction between the ocean and atmosphere, so they simplify. In other words, physics models already sacrifice complete understanding for practical prediction. AI models just make that trade-off more explicit. And there's another factor that might be the real game changer: energy. Remember those billion-dollar supercomputers running for hours? All that computation requires enormous amounts of electricity. By some estimates, AI weather models use roughly 1/1000th the energy of traditional methods per prediction. That's not a rounding error. That's a 3-order of magnitude difference. It means you could potentially run 1,000 AI forecasts for the energy cost of one traditional forecast. Think about what that enables. Right now, global weather models run a few times per day because computation is so expensive. What if you could run them continuously? What if you could run dozens of different models simultaneously and compare their predictions? What if developing countries could run their own high-quality forecasts without investing in supercomputing infrastructure? Weather prediction could become democratized in a way that was previously impossible. And it's not just Google working on this. The field is exploding. Huawei released Panga Weather in July 2023, just a few months before GraphCast. It was one of the first AI models to demonstrate competitive accuracy with traditional systems. NVIDIA developed ForecastNet, which can generate week-long forecasts in less than 2 seconds. That's 45,000 times faster than traditional methods. And here's the really significant development. In March 2024, ECMWF, the organization that runs those 80 million euro supercomputers, announced they're integrating machine learning models into their operational forecasting pipeline. The experts who built the traditional systems are now adopting AI. That's not disruption from the outside. That's transformation from within. Now, I want to take you back to where this all started, because there's a beautiful historical irony here. In 1922, a British mathematician named Lewis Fry Richardson published a book called Weather Prediction by Numerical Process. He had spent years, literally years, attempting to calculate a single weather forecast by hand during World War I. He worked in the ambulance service in France, doing math between transporting wounded soldiers. His forecast for 6 hours of weather was completely wrong, but his insight was revolutionary. In principle, you could predict weather by solving the equations of atmospheric physics numerically, step by step. Richardson calculated that to forecast weather in real time using hand computation, you would need 64,000 human computers, people doing arithmetic, working in a vast hall, coordinated by signals from the conductor at the center, each person calculating the weather for one region of the globe and passing their results to their neighbors. He called this thought experiment a forecast factory. It took until the 1950s for electronic computers to make numerical weather prediction practical. It took until the 1980s for it to become reliably better than simpler methods. It took until the 2020s for AI to begin challenging it. And now here we are. 100 years after Richardson's dream of a forecast factory, we've built something he never could have imagined. A neural network that learned weather from examples instead of equations, runs on a single chip instead of thousands of workers, and produces better predictions in 1 minute than his 64,000 human computers could have produced in a lifetime. So where does this go from here? In the next few years, we're likely to see hybrid models that combine physics simulation with machine learning. Instead of choosing between the two approaches, forecasters will use both. Physics models to enforce fundamental constraints like conservation of energy, AI models to capture complex patterns that are hard to simulate directly. We'll probably see AI weather models specialized for different purposes. One model optimized for hurricane tracking, another for precipitation, another for extreme heat events, each trained on data that's especially relevant to its specific task. And as climate change makes weather more extreme and less predictable, we'll need every tool we can get. The economic stakes are enormous. Better forecasts save lives. They help farmers plant and harvest at the right time. They let airlines avoid turbulence. They help cities prepare for storms. One estimate suggests that every additional day of accurate weather forecasting is worth billions of dollars to the global economy. But I want to leave you with something to think about, because this story isn't really about weather at all. It's about a fundamental question. Do you need to understand something to predict it? For most of human history, the answer seemed obviously yes. To build a bridge, you need to understand physics. To cure a disease, you need to understand biology. Understanding creates capability. AI is challenging that assumption, not refuting it entirely, but showing us cases where prediction can run ahead of understanding, where patterns and data can substitute for knowledge of mechanisms. Maybe that's troubling. A model that works, but that nobody understands feels fragile, untrustworthy, almost like magic. And we've learned over centuries that magic isn't real, that understanding is the foundation of reliable technology. Or maybe it's liberating. Maybe there are problems so complex that understanding them completely is impossible within practical timescales. Maybe pattern matching is sometimes good enough. Maybe the best approach is to combine both, to use physics when we understand the physics, and use AI when patterns outrun our theories. Weather was the testing ground. Protein folding was another. Google's AlphaFold predicted protein structures faster and more accurately than physics-based simulations. Who knows what's next? One thing I'm confident about, we're watching a paradigm shift in how science handles complex systems. And you're going to see this story play out across dozens of fields in the next decade. If you found this interesting, hit subscribe because I'm going to be covering more of these scientific revolutions as they happen. Next week, I'm exploring how AI is transforming drug discovery and why the pharmaceutical industry is either terrified or excited, depending on who you ask. Thanks for watching. I'll see you in the next one.